Alright, this is our introduction to polynomials. And I'm sorry that the video is a little bit fuzzy, but we're going to be working on that. The United States Postal Service will not accept rectangular packages if the perimeter of one end of the package plus the length of the package is greater than 130 inches. Consider a rectangular package with square ends, as shown in this picture. Assume that the perimeter of one end of the package plus the length of the package equals the maximum 130 inches. So let's look at what those options would be. So let's say our width was 10 inches. If the width was 10 inches, then what would be the perimeter of that end? Well, it would be 40, because we're talking about a square one. So the length, if they have to add up to be 130, would be 90, because 40 plus 90 is 130. Our volume, then, would be what? If we have a 10 by 10 by 90. So remember, that's 10 by 10 by 90. That would be 9,000. And remember, that's inches cubed. When we get up to volume, it is inches cubed. Let's say we only had 15 here. 15, 15, 15, and 15. That would give us 60. That means our length here would be a 70. Remember how we're going to find our volume? Width times length. So that'd be 15 times 15 times 70. Which I am going to use my calculator on because I don't know that off the top of my head. So 15 times 15 times 70 gives me 15,750. What about if our width was 20? So remember, we're talking about the perimeter here plus that. So 20 plus 20 plus 20 plus 20, that's 80. And if 130 is our max, that would mean that our length would be 50. So our volume would be 20 times 20 times 50. 20 times 20 would be 400 times 50 would give us 20,000 for our volume. What about 25? 25 for a width would be 25, 25, 25, and 25. That would give us 100 here. That would only leave 30 for the length. For the volume, it'd be 25 times 25 times 30, which is 18,750. Notice the volume is actually going down now. What if the width was 30? 30, 30, 30, and 30, that's 120. That only leaves 10 for the length. That'd be a weird sized box, but that's okay. 30 times 30 times 10. So that would mean this end is a lot bigger than the length going backwards. 30 times 30 is 900 times 10 would be 9,000. What do you think the largest possible volume would be if we had a square end on a package? Well, I would guess around 20,000. It might be more, but around 20,000 would be a good estimate. Now, using the package that we had up there, let's see if we can write an expression for the length in terms of the width of those square ends. So remember what we were doing. We took the width, and it was a square, so we had 4 of those. And then to find out the length, we took 4 times that from that 130. So for the length, you're going to take that 130 and subtract that perimeter of that square, which should be 4 of whatever that width was. So let's think about how we found the volume. The volume, I was taking the width times the length. And we want it as a function of W, which means we don't want any L's in there anymore. We just want W's. So that would give me width times times, and we just wrote an expression for our length using just the variable w. So that's 130 minus 4w. I could clean that up just a touch. W times w is w squared. We could even clean it up even more. Could we distribute? W squared times 130 would be 130 w squared. Now what happens when I multiply w squared times another w? That's going to give me 4w cubed. So last unit we were just talking about quadratics. Now we have a cubic. It's got something cubed. So let's think about the domain of this function. What would be our reasonable values for w? What makes sense in this model? Well, you could have nothing on the width, it really wouldn't make a box. 0. And notice that it went down, the size kept going down here. So what would be our other option? 130 minus 4 times something would be another way to get 0 out of the volume. So what is 130 divided by 4? Well, that would be 32.5. That would be our maximum. Because if you had 32.5 for your width, then 130 would be taken up by that end, and you'd have no length, which really wouldn't be a box. But we need to be between those two values, or else you don't have a box. So your domain would be that the widths have to be between 0 and 32.5, or else you don't have a box. So let's sketch the graph over the domain we just talked about. So let's see. How about 0, 4, 8, 12, 16, 20, 24, 28, and 32. I'm going all the way to 32 because we said that domain had to be up to 32.5. And let's plot some of those values that we had. Well, 0 would be 0, right? Because you couldn't even have a volume. Couldn't even make a box. We had 10, which would be right in the middle of here. We got to get all the way up to our top. So let's make these by, how about 2,000? 4,000, 6,000, 8,000, 10,000, 12,000, 14,000, 16,000, 18,000. And I know I had one that was at 20,000. So that's why I wanted to make sure I went that far up. Remember, these are widths, and this is our volumes up here. So when we were at 10 for width, we had 9,000. So 10 to 9,000 would be right here. 15 for our width, which would be almost to the 16, gave us 15,750. So almost there. When we had 20 for our width, we were all the way up to 20,000. And when we had 25 for our width, we were at 18,750, so somewhere right in there. And then 30 was back up to 90,000. And then 32.5, so right about here, we're going to be back at 0 because we can't even make a box. Now let's look at that as well in our calculator. So I wanted to practice us putting this in the calculator. So the equation was 130w squared minus 4w cubed. So I can't use w, so I'll use x's. 130x squared minus, is it 4x cubed? Now, to get cubed, there's two ways to do it. We can do the up arrow and then put 3. Your other way you could have done that, so I'm going to back up. So let's clear that. Oh, I didn't mean to clear the whole thing, but that's okay. X squared minus 4x. The other way you can put a cubed is under Math. The third option is cubing. So that's another way you can do it. Now we want our window to match our window here. So since W is my x's, I'm going to go 0 to, and I want to include that 32. So under window, it's okay to go a little bit off, so I'm going to go -2 to how about a 34. And for the y's, it's okay to go a little bit below 0, so I'm going to go -10. But I want to go all the way up to 22,000. And our scale was 2,000 on our drawing, so I'll do that there too. I could even make the x scale match what we had on our picture and go by 4s if I wanted. I'm going to leave it like it is. And look at the graph and make sure of what happens. Looks almost like a roller coaster. It starts here, and it kind of does this curve, and it goes up, and it goes up, and then it's turning around. Now, could we find the maximum point up at that top and see if it really was that 20,000 or if it is going like I kind of sketched where it might have gone higher? To find that maximum value, that was under a calculate. So second trace opens up our calculate menu, and there's an option to find the maximum. Now to find the maximum, left bound means I have to have my little cursor to the left of where I think the maximum is, which I do, so I'm going to press enter. Now it says right bound. So we're kind of closing in on the value we think it is. So I go well to the right of it and press enter. And it asks me if I want to guess, and I'm not too concerned about that. But it gives me a maximum at 21.667 for my width and 20,342.593 for the y value. Now remember, that would be the volume that goes with that width. So to get the maximum volume out of those restrictions, your width of your box would have to be 21.667. If you went further than that, up to 22, you're already going down on the volume you have. Or if you're at 21, you're at your volume isn't going to be as big as that point. That is the maximum value. So when we're talking about it, the coordinates that give us a maximum value are that our width has to be 21.667. Now, that model we were looking at was actually a cubic, which is a type of a polynomial function. We have been dealing with polynomials for a long time. A polynomial means that you have coefficients on each of your terms and an x to some power. And we always write them in descending order. You always want your biggest exponent first, and then they go down from there. Another thing is that your exponents have to be non-negative, and they have to be integers. Now technically, you would have one of x to the 0. And let's think about what that means. X to the 0 would be 1, so that's what you actually have on your constant. It's kind of an imaginary x to the 0. It's the smallest exponent you can have for x. It's just not there because anything to the 0 power is 1, so we don't even write it. But it's all terms that have an x to some exponent with a coefficient. Notice each term is being separated by addition. Technically, this is plus a -3. So they are all being separated by addition. The degree of the polynomial is the biggest exponent. So let's look at some math terms. Each of these. So if we had a function with a degree of 0, that means your largest exponent is a 0. In other words, you don't even have an x. So an example of that would just be f of x equals 1. No matter what you put in for your x, you get the same thing out. So that's why it's called a constant. Linear. Your largest exponent is going to be a 1. So x to the 1, but we don't really put the 1 there because it's kind of understood that if you just have an x by itself, its exponent is 1. And so this would be an example of a linear. The highest degree is a 1. Quadratics, which we just got done studying, have a largest exponent of 2. So that would mean we'd have something x squared. And the next term would be an x. And then we could have a constant. Now, do we have to have everything after that, or could you just have an x squared? You could. All this is saying is that this is the largest exponent we have. Cubic means we have something cubed. So, kind of like in our example with the width squared, you end up with something x cubed. And it could be as simple as just 4x cubed. There's another one called quartic. And that just means you have x to the 4th. And notice how I didn't put a coefficient in front of there, but that just means the coefficient would be 1. All right, on this next one it says we're going to take the same rule, function rule that we had in the situation and look at it not defined over that restricted domain of the problem, but defined on all real numbers. So that would be f of x equals negative 4x cubed plus 130 x squared. Now notice I wrote it with the largest exponent first. This would be a third degree polynomial because its largest is a 3, so this is considered third degree. And one thing we always want to notice is what our leading coefficient is. The leading coefficient is the number in front of the variable with the largest exponent. So the leading coefficient of this problem would be a negative 4. Now we already had put it in our calculator, but we were looking only at that restricted domain. So I'm going to look at my table and find values to fill this in. Now on my table, it's not starting where I want it to start because I need to start all the way at negative 40. And you notice that it's counting by 5s along here. So I'm going to count by 5s. And I'm going to go to the table. Negative 40 goes to 464. That's way too big. Let's see where I can start graphing, because this goes only up to 35,000. Oh, here we go. At negative 10, we are at 17,000. Notice at negative 15, we're way above the graph. At negative 10, I'm at 17,000, which would be about here. At negative 5, I'm at 3750. So here would be 5,000, so that would be about here. At 0, we were at 0. Remember, that was because the box wouldn't even have a volume at 0. At 5, I'm at 2750. At 10, I'm at 9,000. At 15, I'm at 15,750, which would be about here. 20 was at 20,000. 25 is at 18,750. So it's going back down a little bit. 30 was at 9,000 again. That would be about here. And then by the time we get to 35, we are negative 12,000. And 40 is at negative 48,000, so it's way down here. So our graph would end up looking something like this. It's like a little roller coaster. Now notice, if we stretch out our domain to be all real numbers, now our graph will keep going on and on forever, left and right. Also, the ends keep going up and down. So we actually keep going on and on forever in both directions. So there's not truly a maximum value because it keeps going up and up. And there's not truly a minimum because it keeps going down and down and down. But what we there's things we call relative maximums and minimums. This point right here where we have this up on our roller coaster is called a relative maximum. There's no true maximum because the graph keeps going up and up and up. But as far as what we're looking at within here, this is a relative maximum. And we actually found that value earlier. The maximum value was the y that was at that point, and it was 20,343 for just approximately. So I'm going to put approximately. The relative minimum would be this point where it dips down here. This is called a relative minimum. Because as far as the graph goes, that's a dip. The relative minimum would be the y value for that point, which would be 0. Now, let's think about where the x-intercepts and y-intercepts are for this graph. Those questions, this was question 9 on your packet. I'm doing everything looking at this graph, so I'm just going to keep this in view. But on number 9, you were supposed to say what the relative maximum was, which is 20,343. And the relative minimum is 0. It's the y values for those points. Now, our x-intercepts, remember, that's what makes your y value 0. So we've got 1 here. We've got an x-intercept at 0. And then we had another one over here. And remember, there was another value that gave us a volume of 0, and it was 32.5. Our y-intercept is the point where x is 0. Well, we just happen to have it crossing at the origin, so our y-intercept is 0 as well. Now, we also want to talk about end behavior. End behavior is what's happening at the ends. So we think about what happens as x gets really, really big or as x gets really, really small. So looking at this graph, what is happening as x gets really, really big? Now, the biggest number I can think of is infinity. So we talk about what happens as x approaches infinity or gets really, really, really big. So if I kept going on my graph, think about what kind of numbers I was getting as I got bigger and bigger in my x's. They kept getting smaller and smaller and smaller and smaller and smaller. What are they going to finally approach? Well, if they keep getting smaller and smaller and smaller, they're just going to be the smallest thing I can ever think of. So another way to think about this is the right side of the graph when x goes to positive infinity. We think about which direction our graph is going. Well, it's going down. So going down, it's going to keep going down forever until it reaches negative infinity. Now, if we also look at the left side, our x values are going to get smaller and smaller and smaller and smaller and smaller and smaller until they get to negative infinity. And look what the graph is doing. As we get smaller and smaller in our x's, our graph is going up and up and up and up. How far is it going to go? Well, it keeps going on forever, so it's going to positive infinity. And if you like, you can put positive infinity so you remember it's plus, and that means it keeps going up and up and up and up. So let's copy those on to over here at number 11. We're thinking about what happens to the function as x gets really, really big and as x gets really, really small. So this one was as x approaches positive infinity, f of x was doing what? It was going down. So it goes to negative infinity. When we look at what happens on the left side as x gets smaller and smaller and smaller and smaller, f of x was going up. So it was approaching positive infinity. Now let's think about the function 3x squared minus 6. What would that look like without even having to look at the calculator? Well, it's a quadratic, and it's positive, so it's opening up. It's got a vertical stretch of 3, and it is down 6. So it would have been down 6, stretched, so it would be opening up like this. Now remember, they keep going on and on forever. So what kind of behavior does it have on the right side as x approaches positive infinity? Well, it's going up and up and up and up. So f of x would keep going up and up and up and up to get to positive infinity. If we look at the left side, as x approaches negative infinity, f of x is going up and up and up and up as well. And the graph is the easiest way to really think about what's going on here. So let's think about some of these graphs. And let's use a calculator to look at them quickly. Now, we have played with the window before. So now let's get our window back to normal. So if I go to zoom, I'm going to go back to a standard window. We're going to do quick graphs and think about what's happening with the end behavior on each of these. Now that was our other graph and we want to get rid of him. We're going to clear it out. The first one we're going to look at is the function y equals x squared, which I hope we don't even need a calculator. Y equals x squared was that parabola that's going through the origin. That was our parent function. And notice it goes up and up and up and up. So either direction it's going up. What happened when we had negative x squared? Well, it reflected over the x-axis. So that's going to change that end behavior to going down and down. Now let's look at x cubed. This would be the parent function for the cubics. Remember, there's two ways to get to cubed. I'm going to do it with the caret button and then do 3. And let's look at the graph of the parent of x cubed. Notice it came in, and instead of doing the roller coaster thing, it just kind of did a little slide there. Started down, and then went shoop, and then went up. So on the positive side, it gets bigger and bigger and bigger. On the negative side, it gets smaller and smaller and smaller, more and more negative. If we do negative x cubed, let's think what's going to happen. Well, we said negative reflects over the x-axis. So I'm thinking it's going to reverse it. Try it out. Negative x cubed. Oh, it does flip it. So it's going to change that direction. It's going to flip it. Let's look at x to the 4th. X to the 4th. So I used the caret button to get up in the exponent, and I put 4. And kind of looks like a parabola. It's actually coming down and doing a little, it's like it's flatter at the bottom. But it behaves kind of like what x squared does. What's going to happen when I do negative? What's going to flip it? So it's got the same type of shape. What's going to happen when I do x to the 5th? Well, I'm going to type it into my calculator so we can look at it together. X to the 5th. It's even more flatter than the x cubed. So it comes up, and it's kind of sitting, got a little flatten out there. But it's doing what x cubed does, it just does something a little bit different in the middle. So I bet if I make it negative, it's going to just go the opposite direction. So what do we think is happening with end behavior? Well, x squared and x to the 4th behave the same. Their end behavior was always going in the same direction. X cubed and x to the 5th did the same things. So let's make a conjecture about the end behavior of, let's start with x to the 10th. Which one do you think it's going to behave like? X squared or x cubed? Well, x to the 10th is even, so it's going to behave kind of like that, but it's probably going to be really flat. So my end behavior as x approaches infinity, to the right side, f of x also gets bigger and bigger and bigger. So it goes to infinity. I should have said y because we're talking about y's, but that's okay. We'll change it to a y. When x gets really small, what happens? Well, again, it's going up and up and up. So it goes to positive infinity. What would happen, I did it again, if we had negative x to the 20th, still even, so it would flip it. So what would be your end behavior? It would be flipped. It would be going down and down and down. So both directions are going to negative infinity. Let's think about what would happen if we had a function of x to the 19th. Now it's odd. So it's not going to behave like x squared or x to the 4th. It's going to behave more like x cubed and x to the 5th. So it's going to look something like this, which means as x gets bigger and bigger, so the right side, it goes up and up and up. But if we look at the left side, when x gets smaller and smaller and smaller, the graph is going down and down and down. What would happen if we flipped it? Well, it would literally flip the graph. This time, on the right side, as x gets bigger and bigger and bigger, y is going down. On the left side, it's going up. So it just reverses which way our end behavior is going.